Let's take a look at an example of convolution. We'll do the one that's in the notes, but I'll use a different approach from the one that's in the notes in case some people find that graphical approach that I took there confusing. So let's suppose that we're convolving the following two one-sided functions. F of t is effectively a rectangular pulse. It's equal to 1 when little t is between 0 and big T, but otherwise it's 0. And g of t is a one-sided decaying exponential, e to the minus t times the unit step. So by definition, using the one-sided convolution formula, the convolution is given by this integral. The integral from 0 to t of f of tau times g of t minus tau d tau. We looked at a graphical way of considering this integral in the lecture notes. In this lecture, I'm just going to solve it analytically. So suppose we want to perform this integration. Well, there are two cases to look at, really, because if little t is less than big T, then by definition of f of tau is just going to equal 1 throughout this interval from 0 to t over which we're integrating. So in that case, this f of tau will always be equal to 1. So let's consider that case first. If little t is greater than or equal to 0 but less than big T, then our convolution, which is the integral of tau from 0 to tau of f of tau g of t minus tau d tau. We can simply write, that upper limit should be t rather than tau. And if t is less than big T, then our rectangular pulse f of tau is always going to be 1 throughout the interval over which we're integrating. So this will simply be the integral of g of t minus tau d tau. And that will be e to the minus t minus tau d tau. So we can take out a factor of e to the minus t because we're integrating with respect to tau. So we simply have e to the minus t times e to the tau d tau. So for this case where little t is less than big T, f star g of t is going to be e to the minus t times e to the tau evaluated at t minus e to the tau evaluated at tau equals 0. So that'll be e to the minus t times e to the t minus 1, or in other words, 1 minus e to the minus t. So we could start sketching our convolution. We've found out what it looks like when the value of little t is between 0 and big T. And in that case, it looks like 1 minus a decaying exponential. So that's going to look like this, where this value that it reaches here is 1 minus e to the minus capital T. So that's the first part, if you like, of the plot of our convolution for small values of little t. Now, what if little t is greater than big T, greater than or equal to big T? In that case, our convolution which always has this form. Well, can always be written in this form. What's it going to look like? Well, when little t, given that little t is greater than or equal to big T, and f is 1 only for values of its argument that lie between 0 and big T, f is going to become 0 as soon as tau gets greater than big T. So in fact, we might as well just integrate with respect to tau from 0 to big T. If we let tau get greater than big T, f is going to vanish, so our integrand won't contribute anything more to the integral. And of course, if we're only integrating between 0 and big T, then f is only going to be equal to 1 throughout that interval. So once again, we're just integrating g of t minus tau d tau. In other words, our convolution is going to be the integral of e to the minus t minus tau d tau, but this time integrated between 0 and capital T. We can once again take out a factor of e to the minus t, since we're integrating with respect to tau. So we get the integral of e to the tau d tau integrated from 0 to t. So for t greater than or equal to big T, our convolution is going to be e to the minus t times e to the capital T minus 1. Okay. Another way of writing this is e to the minus t minus capital T times 1 minus e to the minus capital T. And it's useful to write it in this way because, going back to our graph, 1 minus e to the minus t is precisely the value that the convolution tends toward as t approaches capital T from below. That's precisely this factor that we have here. So starting at that time when little t is equal to capital T, the value of the convolution simply decays exponentially from this value that it reaches at t equals capital T. This is just, as a function of t, this is just a decaying exponential, if you like, that this term here has the value 1 at little t equals capital T, and then it decays exponentially. So the whole function at t equals capital T has the value 1 minus e to the minus capital T. So the graph, in fact, looks like this. This being e to the minus t minus capital T times 1 minus e to the minus capital T. So this then is what we arrive at as our convolution in this example. Later on, when we start looking at systems and signals, you will probably come to recognize this as the response of a so-called first-order system to an input that has the form of a square pulse. As I say, we will look at convolution much more when we get into signals and systems. They're particularly important for signals and systems. And these diagrams will start to look, these plots will start to look much more familiar at that point. For now, let's simply state the property of our Laplace transforms that relates to convolutions. suppose that there exist real constants, alpha and beta, such that the two integrals e to the minus alpha t dt times the modulus of f of t and e to the minus beta t dt times the modulus of g of t exist. Then the convolution of f and g exists. And the Laplace transform of that convolution turns out to be simply the product of the transforms of f and g. So the counterpart of multiplication in the Laplace domain is convolution in the time domain. This will turn out to be an important property for differential equations, but especially for signals and systems. So we'll come back to that later. For now, this is another addition to our list of properties of the Laplace transform. See you next time.